Okay. So we're going to cover here a problem-solving section. Integrals calculus and total accumulation. What they're trying to do here is we've spent a long time now teaching you about what the fundamental theorem of calculus is. This section is to show you what it does for you, what it means to the business person, what it means to someone going into your field. Okay? Here's the key idea from this section. I'm going to sum it up on one slide. Suppose f is a continuous rate function. Now, what do I mean by that? Well, remember on the homework, little b of x was the rate of change, right? A rate of change. If you have a little f is a rate of change function, and big F is the antiderivative of little f, well, then we know we can integrate, right? This is what the fundamental theorem says. But now here's what it means. What it gives you is the total accumulation of big F from A to B. The total accumulation. So in that problem we had for homework today, what did little b of x stand for again? I can't remember. It was bankruptcies. It was the rate of change of bankruptcies. What this section tells us is that when you integrated, when you found the antiderivative, what you were really doing is finding the total number of bankruptcies. That's what you're getting. Okay? Now I'm going to walk you through a few examples, a couple sample problems right from the book that'll kind of spell this out. Okay, so let's start with problem 20. The instructions are to evaluate and interpret this integral. They give you this function, but what I think the most important thing is to interpret. So I'm going to pause while you read. We're going to want to write down what x stands for and what the function r stands for. Okay, so let's write down what we know. What's x mean here? Years since 1980. What's r? A rate, right? Actually, we had this lotto example before. This is the rate of sales. So it's a derivative of something, right? And what are the units? So it's billions? Oh, millions of dollars per year. Okay? So when I said this is a derivative of something, it's with respect to x, because x is years, and that's the denominator. The numerator should be something in millions. Now, you might remember, we did this as an example the other day, and it was ds dx, where s stood for sales, all right? Now, I don't need that for this problem. It doesn't actually say I need that. But r of x actually is a derivative of some other function. Do you remember that? Because it's a rate of sales, so it's the derivative of the sales. That's the idea. S is sales in millions of dollars. Okay. So they want me to evaluate and interpret this integral. Fine. You could work it all out. You'd get a cubic. I don't want to spend the time doing that. I'm going to type it in the calculator to save time. And then what I do want to spend the time on is interpreting. So let's see. Negative 14.58 x squared plus 186.84 x plus 383.93. Now if I graph it, I don't see very much, right? I want to change my window. So I'm going to change my window. Well, what about x min and x max? What do you think? Well, we want to go from 0 to 16, right? At least. So let me do that. 0, 16. Okay? Let me graph it now. Still don't see very much. And that's okay. Here's what I want to do. I want to integrate from 5 to 10, just to see what happens. I know I can't really see it on the picture, but that's okay. I'm going to just do it anyways, because I'm imagining you guys on, say, a quiz or a test, and or on your homework. You're trying to do this. You can't get the window right, but you can always get the x min and x max right because we're on a certain interval. So let's see, 5 to 10. So I go down to choice 7, and I integrate lower limit 5, enter, upper limit 10, enter. So it finds the area under the function from 5 to 10, and I got this value, 4673.65. 4673.65. Okay, I evaluated it. How do I interpret it? That's the question. Well, what you do is you look this way. R of x is a rate of sales, right? It's a derivative. It's a derivative with respect to x because the units were millions of dollars per year, and years is x. So now you say, well, what is it the derivative of? If it's the rate of sales, it was the derivative of the sales function. Does that make sense? So when I do the integral, what's this giving me? It's giving me, now according to what this says, yeah, I said it's the total sales. It's the total, see if you look back at the key idea, it's the total accumulation of big F. Big F in this problem is big S, which is sales. And now from A to B, so since it's 0 since 1980, this is what Andrew's saying. She's saying, well, total sales from 85 to 90 was, okay, what? $4,000 million. Okay, so $4,673,650,000. It's the total sales. Weird. The area under the rate curve gives you the total sales. How do I make sense of that? I think I'll help you when I do the next example. I think you'll see a little more why that area is in fact the total sales. Okay, so in problem 40, they write the function v of t is negative 32t plus 88. This is more of a science application, but I think it's a nice one to help your understanding. You know what v stands for? Velocity at a time t. Here, t is time in seconds. And v is velocity. How do you measure velocity? On my car, I measure it in miles per hour, right? Now, the units here are seconds, so I don't want to do hours. So I could do miles per second or meters per second. Turns out that I know for a fact when they wrote this, they intended it to be in feet per second. And the reason I know that is because this is an important number in physics, negative 32 feet per second. Actually, per second per second. Per second squared is the acceleration of gravity. Okay, that's what this is. But anyways, what this models is this models a falling object. Okay? And what it does is it tells you how fast the object is moving. Actually, this is an object thrown up in the air. That's what it really is. So if you threw an object up in the air at a certain speed, actually I know what speed it is too. This would tell you what happens to the object over time. How do I know that? Well, by the way, what's the initial speed? What is v of 0? Well, it's 88, right? So that says we threw the object up in the air at 88 feet per second. Over time, what's going to happen to that object? Well, the speed is going to slow down, right? So like, what's v of 1? Or let's do v of 2, let's say. Well, that would be negative 32 times 2 plus 88. So after 2 seconds, is it still going up? Well, yeah. But it's going up at 24 feet per second instead of 88 feet per second. You guys see that? After 3 seconds, is it still going up? Not anymore, right? See how it's negative? I don't know what it is, but it's negative. Now it starts coming back down. So gravity is going to slow the object, and then it's going to start pulling it down. And it'll pull it down faster and faster as time goes on until it hits something. You guys follow the idea? Okay. So now what I'm going to do is I'm going to integrate v of t. You're not going to put dx here. You're going to put dt because that's my input. So let's integrate negative 32t plus 88 dt. Okay, so when I integrate, what do I get? Negative 16t squared plus 88t. Okay? And that's a parabola. And the shape, if you ever did a graph of where an object is versus time with gravity, you probably got a parabola. The problem that we're actually doing here, part B of the problem, says let's integrate from 0 to 2 to see what happens during the first 2 seconds. So that's what I'm really doing. So I get negative 16 times 2 squared plus 88 times 2. So I get negative 16 times 4 plus 88 times 2. So I get negative 64 plus 176, and that's 108. What are the units? 108 what? Not feet per second. Velocity was in feet per second. Why is it just feet?
Because this is travel and velocity is weight.
So this is the total distance traveled in feet. That's right. This is a rate function in feet per second. It is, if you want, let's call it dx dt, where x is the position function, position in feet. But the point is that It's this numerator that you're going to get when you integrate. And you're going to get the total accumulation of the numerator. So it's the total number of feet. All right, I'm out of time.